So guys, like I said, let's take another example to help illustrate what we have said in the other page. So a mass of 0.9 kg of fluid initially at a pressure of 15 bar, a fluid here again, so note that, and a temperature of 250 degrees Celsius expands reversibly and polytropically. So this is a polytropic process. Polytropically to 1.5 bar. Find the final temperature, work, heat transfer, and change in entropy if the expansion index is 1.25. Yes, it sounds difficult, of course, but you firstly you write your parameters that way, it will not look difficult again. So parameters given, so we have our expansion index n, which is 1.25. We have the mass m, 0.9 kilogram. We have P1 initially to be 15 bar, T1 250 degrees C, which is 523 Kelvin. Okay, and then P2 1.5 bar. So for a polytropic process, we have a diagram like this. Okay, here is 2, here is 1. This is PV raised to power n constant. So P1 raised to power 2.5 should be equal to P2 V2 raised to power 1.25. Okay, now having done this, we'll make our necessary assumption. Since it's a fluid, now assuming the fluid was a steam, we are going to have that m 0. This P1 is equal to what? 15 bar at T1 equal to 250 AEC. So as usual, you go to the saturated vapor table and check for the temperature of the temperature at 15 bar. So from the saturated vapor table at P1 equal to 15 bar, the corresponding temperature is 198.3 degrees C. So that means T1 is greater than Ts, hence it's superheated. So if it's superheated, you go to the superheat table. So from the superheat table at P equal to 15 bar and 250 degrees C, we have that U1 is equal to 2697 kilojoules per kilogram. We also have that S1 is equal to 6.711 kilojoules per kilogram Kelvin. specific volume is 0.152 meter cube per kilogram. So from our polytropic law, we have that this is this and that is that. Okay, so V2 over V1 is equal to 1.25 will be P1 over P2. Okay, so V is specific is what I use for specific. So V2 we go to 0.152 into 15 over 1.5 1 over 1.25. That is indices. Once you move the power over, divide by 1. Okay, so what do we have here? Finally, specific volume in the second state is 0.959 meter cube per kilogram. So with that, we can find what was requested, the question. So final temperature is the temperature at 15 bar. The final temperature, okay, the final temperature T2 is the temperature at P2. What is P2? Okay, what was our P2? Okay, P2 is 1.5 bar, not 15. 1.5 bar. So the final temperature is the temperature T2 at P2. So from the saturated table, if you go there, go to 1.5, you find the corresponding temperature. You will see 111.4 degrees C, and that is the final temperature. So the work, the polytropic work will be equal to P2V2 minus P1V1 over N minus 1, but we have a mass, so we multiply it by our mass. So work will now be 0.9. P2 is 150, converting bar to kilopascal. To make your necessary conversion, you confirm this, minus converting 15 to kilopascal 2 times, okay, let's use a valid bracket, not have numerous brackets. Okay, so we'll have that this is 1,5 times 0.152. okay, all over 1.25 minus 1. So finally work done will be minus 75.735 all over 0.25, which will give us minus 302.94 kilojoules. That will be our polytropic work. Okay, that will be our polytropic work. So now, still at state 2, state 2, P2 is equal to 1.5 bar, Now we don't have any temperature, we don't know if it's superheated. How are we going to get the other parameters? So, but remember that we have found V2, specific V2 here, which is 0.959 meter cube per kilogram. Scroll up, you will see it. So now from the saturated vapor table, we have that at the pressure P2 1.5 bar, Vg is equal to 1.159 meter cube per kilogram. So as we all know, specific volume is this. So x2 will give us 0.959 over 1.59, which is 0.827. Now with this we can find our U2, because we are not done, so we should find the work and also the heat transfer. Okay, so for us to find the heat transfer, you will need, since Q plus W is equal to U2 minus U1, we have gotten the polytropic work, so we need this. So we've gotten this, we need this to find what the heat. So having done this, we can say U2 is equal to UF plus X2 UG minus UF. So at P2 1.5 bar, yeah, at the saturated vapor table, you have your UF to be 467 plus X2 is this, UG is 2519 minus 467. So finally our U2 will be 2164.0 kilojoule per kilogram. Similarly, S2 is equal to SF plus X2 SFG. So from the saturated steam table 2 at the same value, we check for the SF, and the SF 1.1434 plus 0.827 into 5.789. So you have your S2 to be 6.222 kilojoule per kilogram. Okay, I think we can find the heat now. The heat transfer, which is the third question. Heat transfer, remember that heat plus work is U2 minus U1. So heat will be U2 minus U1 minus polytropic work. So the U2 we got, remember we have a unit mass, so M. So what was the M given? 0.9 times changing U, that's 2164 minus what was the U1? U1 was 2697 minus polytropic work, this is minus 302.94. So this implies that summarize that. This page is finished, so I'm going to open another page. Let me finish it here. Q will be equal to minus 176, or I say 0.9 times minus 553 plus 302.94, which will give us minus 176.8 kilojoules. So as you can see, this is what we have. So I'm going to open another page. So just like I said before, the heat is what? 0.9 into 533 plus 302.94, which gave us was minus 176.76 kilojoule. So the negative sign indicates ejected heat. The negative sign indicates ejected heat. So the fourth question was the change in entropy, which S2 minus S1. We have the value of our S2 and that of our S1. So once you subtract, you have minus 0.489 kilojoules per kilogram. But we also have a unit mass, so including our unit mass, we have 0.9 times this value. So change in entropy will give us minus 0.4401 kilojoule per kilo, per Kelvin, because mass has cancelled out. So this is just for the assumption of the fluid being a vapor or a steam. So assuming it to be a perfect gas, assuming the fluid to be a perfect gas, or assuming the fluid a perfect gas, so assuming it were a perfect gas, we have that. Remember that P1 is equal to 15 bar, T1 is equal to what? 250 degrees C, which is equal to 523 Kelvin. Now our index is 1.25, so T2 over T1 is equal to P2 over P1 raised to the power n minus 1 over n, So we have the value of T1, that is 523, and P2 was 1.5 bar, so P2 is 1.5 bar over 15 is per 0.25 over 1.25. So finally, doing the necessary calculations, we have that T2 is 329.99 Kelvin, which is approximately 330 Kelvin. So we have found the second temperature, that is the final temperature. The final temperature I was asked in the question. So let's go back and check. They asked for the final temperature. Okay, the final temperature, we've gotten it. We've gotten our final temperature. So you can see that final temperature T2 is equal to 330. So the next one is the work, polytropic work. So polytropic work. So remember, for the steam, polytropic work was P2 V2 minus P1 V1 less M times this. So but PV is equal to what? MRT. So this is for steam. So for perfect gas, polytropic work will be M R T2 minus T1 all over N minus 1. So polytropic work will be, what was the mass? 0.9 times R is 0.87, T2 is 330 minus this. I have what? 1.2. We have here is 1.25 minus 1. So WP becomes minus 199.42 kilojoules. So our polytropic work is minus 199.42 kilojoules. So the next is the heat. So from first law, know that you know that Q plus W is equal to U2 minus U1. Okay, now where U2 minus U1 is equal to MCV T2 minus T1. Okay, now the heat transferred Q will be equal to MCV T2 minus T1 minus polytropic work minus polytropic work. So we have that Q is equal to 0.9, the value of CV, a specific heat at constant volume. Then T2 is 330 minus 523 minus 199.4. Okay, yes, of course that was our work done. So finally heat will be 74.68 kilojoules. So choose to write positive. So the positive indicates heat gain. Okay, so lastly, the entropy, change in entropy, which is S2 minus S1, is equal to CV ln T2 over T1 plus R n minus 1 ln T2 over T1. So when you input the value of R, CV, and T2 and T1, you have that change in entropy will be 1.78 kilojoules. Okay, kilojoule per Kelvin, because there's a mass here. So when you multiply it by the mass, you will get that. So we've solved the question, assuming we are a steam, and also assuming that it were a perfect gas. So we have come to the end of today's episode. Stay tuned for more. So in the next episode, we'll be talking about the isothermal process, which is the constant temperature process. So in the meantime, have a nice day and stay tuned for the next video. Thank you so much for your time. Goodbye.
A little liquor and some ladies, yeah. We they turn up on a daily. It's how I walk up, yeah. Soft walk,